Normal probability distributions form the basis of many statistical methods. In this video, we'll look at the properties of normal probability density functions. Normal probability density functions have a familiar bell curve shape. Suppose we have a random variable, we'll call it x, whose probabilities are found as areas under a normal probability density function. We say that x has a normal distribution. The normal distribution is sometimes also called the Gaussian distribution. If our random variable x has a normal distribution, we know then that x is a continuous random variable. And the interval of values it can be is anything from -infinity to +infinity, but most of the probability is concentrated in the middle. Many measurements follow this kind of distribution, where the observations are most likely to be close to a central value, and values become less likely the further away they are from the central value. Even though it's impossible for most measurements to cover the entire range from -infinity to +infinity, and for some variables, like for example birth weights, they can't be negative, they can still have their probability described well by a normal distribution. Because the extreme values, the probability of values out of the range of the normal birth weights, is so small it's close enough to zero to treat it as such for all practical purposes. The normal distribution is symmetric and unimodal, and every normal probability density function has a bell shape. But this bell shape can be more narrow or more spread out, and the peak of the bell can be at any particular value. Like all density curves, the total area under each of these has to be 1, and the actual value of the density function doesn't really matter. It will be areas above intervals under it that are used to calculate probabilities. In order to describe a particular normal distribution fully, we need two parameters, one for the location where the peak is, and one for how spread out it is. As is usually done for statistical models, we'll use Greek letters for the parameters of the distribution. The symbol for the value of x where the center of the bell curve is located is the Greek letter mu. Mu is also the expected value, or the mean, of a random variable x that has this distribution. We'll almost always call mu the mean of this normal distribution. And because the normal distribution is symmetric, the probability of being above the mean is a half, and the probability of being below it is also a half. Our second parameter tells us how spread out our bell curve is. This is reflected by the standard deviation of the random variable x, and its symbol is the Greek letter sigma. The larger sigma is, the more spread out the normal curve is. For a random variable x with a normal distribution with mean of mu and standard deviation of sigma, we write x tilde, meaning x has this distribution, n for normal, and then the values of our two parameters, mu and sigma, in brackets. For a random variable with a normal distribution, about 68% of the probability is within one standard deviation of the mean. So this middle area from the mean minus one standard deviation to the mean plus one standard deviation is 0.68. If we extend this to two standard deviations from the mean, we cover 95% of the area, so the probability of being within two standard deviations of the mean is 0.95. And going out 3 standard deviations from the mean covers 99.7% of the area, almost all of it. These probabilities are for the middle of the normal distribution. Often in statistics, we're interested in values at either end. These are called the tails of the distribution. If we observe data whose possible values follow a normal distribution, we'll expect that almost all of the data will be within 3 standard deviations of the mean, our 99.7%. It is possible for observations to be 4 or maybe 5 standard deviations from the mean, but these would be rare. They would be far out in the tails of the distribution. The standard normal distribution has a mean of 0 and a standard deviation of 1. It is usual practice to use the variable name z for a random variable that has a standard normal distribution. Any other normal random variable can be transformed to a standard normal random variable by subtracting its mean and dividing the result by its standard deviation. So if x has a distribution normal mu sigma, then if we take x, subtract mu, and divide the result by sigma, the resulting random variable has a normal distribution with mean 0 and standard deviation 1, in other words, the standard normal distribution. Random variables with normal distributions have one more property that might seem natural, but it only holds for some probability distributions. If two random variables are independent and they have normal distributions, their sum also has a normal distribution. And if we multiply a normal random variable by some constant, some numerical value, the result still has a normal distribution. This becomes important because a consequence of this is that when we average normal random variables together, the average still has a normal distribution. We need to be a little bit careful with what the mean and the standard deviation are, but this is a useful result. Normal distributions provide useful probability models for random variables in many situations. For example, they can be used to describe the behavior of individual observations when something is measured on each member of a population. They are also commonly used to model measurement error in some kind of measurement process. And many statistical methods are derived from the normal distribution. And many of these methods can be shown to work quite well even if the data aren't quite normally distributed. So it's important to understand the properties of normal distributions.